This video lecture is for section 5.5 of Math 311, a course on linear algebra at Western Illinois University. So we are finally going to look at some applications of all the theory that we've been doing with eigenvalues and eigenvectors and diagonalization and whatnot. And this first application you might not think is a real, maybe a technically real world application, but it has to do with binary quadratic forms. And if you've had multivariate calculus, you've had some experience in them. You've probably had to graph stuff like, an equation like, z equals x squared over 3 minus y squared over 2 or something like that. And this expression right here on the left, this is an example of a quadratic form or a binary quadratic form. So what a binary quadratic form is a polynomial in two variables where basically it's just the degree of each term is 2. So the combined degree of each term is 2. So we have just an x squared term, an xy term, and a y squared term. Okay. So if a, b, and c are real numbers, this expression right here is called a binary quadratic form. And you can also identify it as a function in two variables, okay, x and y. And the as a function, if we can plug real numbers in for x and y, and if it turns out if we always get a positive number, as long as if we plug a non-zero pair x y into this expression and we always get something positive, then we say that this is a positive definite binary quadratic form. If we always get negative values when we plug x0 and y0 in, then we say it's negative definite. And if sometimes we get positive values, sometimes we get negative values, then we say it's indefinite. Okay. And we're going to see how we can there's a neat way of determining if a quadratic form is positive, definite, negative definite, or indefinite, just by looking at the eigenvalues of a certain matrix which is associated with this binary quadratic form, and it's right here. Because it turns out that this expression can actually be written as a product of matrices, where we have this matrix MF, pardon the expression, but that's what we call it, A, B over 2, B over 2, C, and it turns out if we multiply it on the right by the variable vector xy, and multiply it on the left by the row vector xy, then we get then if things come out, we get a one-by-one matrix, and where this is the only entry. Okay. So one thing you'll see about this matrix is that it's symmetric. You can see it very clearly. It's symmetric because B over 2 are here. It's real, so it's orthogonally diagonalizable. So that's lucky for us. That means we can find an orthogonal matrix Q and a diagonal matrix D such that Q transpose times MF times Q equals D, where D is a diagonal 2 by 2 diagonal matrix, where the diagonal elements are lambda 1, lambda 2, and of course we know that the eigenvalues here are going to be equal to the eigenvalues here. So the lambda 1 and lambda 2 are the eigenvalues of m sub f, and they are real because this is a symmetric matrix. And we also can see that we can get Q by just finding the eigenvectors for lambda 1 and lambda 2 and normalizing them so their length is 1, and then these will be the columns of this orthogonal matrix. Okay, so we already know that. But now we have this, something very nice happens. And that is, if we make a little change of variables into this binary quadratic form, it gets even nicer. In fact, we can eliminate the xy term. So we define a new variable x prime y prime, defined to be the q transpose or q inverse times xy. And that is the same thing as saying that q times x prime y prime is equal to xy. And so what will be, we can rewrite this in terms of the entries of q. But when that happens, then this binary quadratic form, which we already know is equal to this, we can replace xy with x prime y prime qt, and we can replace this xy with q x prime y prime here. So this is just a substitution. Okay, but then qt mfq is just equal to d, the diagonal matrix. And remember, d is lambda 1, 0, 0, lambda 2. So then this just becomes lambda 1 times x prime squared plus lambda 2 times y prime squared. Okay, so this is a very important, we've essentially eliminated the xy term. Okay, so what we immediately see here is that any number that's in this form will also be in this form, and every number in this form can be put in this form. So the values of ax squared plus bxy plus cy squared are the same values of lambda 1 x squared plus lambda 2 y squared. Okay, we obviously the xy here is going to be different. It'll be x prime and y prime, but the thing is we can find numbers, given any number in this form, we can find some numbers xy such that this number is equal to this number. All right. Now, we also can see that, well, we'll come back to this in a moment, but we now see that it's very easy to find just figure out if this is, when this will be all positive and all negative. Obviously, if lambda 1 and lambda 2 are both positive, this will always be positive. And if lambda 1 and lambda 2 are both negative, this will always be negative. Okay, except when you're plugging in 0, 0. And then, of course, if one is positive and one is negative, then obviously this can, sometimes this will be positive, sometimes this will be negative, right? We can just, if one of these are variables, 0, then it's very easy to see what this will be. All right, so what we've done is prove this first fact, that if f is positive definite, if the eigenvalues are both positive, it's negative definite if the eigenvalues of mf are both negative, and if they're indefinite if they have opposite signs. Now we get something even nicer. We get a bound. Remember, lambda 1 and lambda 2 have to be real, so one's going to be bigger than the other. So let's say if lambda 1 is less than or equal to lambda 2, and if we have the constraint that x squared plus y squared equals 1, then we can see that this expression is always bounded between lambda 1 and lambda 2. Okay. Now, I think we can see that because if we put a restriction on, the main idea here is that because Q is an orthogonal matrix, remember x squared plus y squared equals 1, if and only if x prime squared plus y prime squared is equal to 1. And that's since Q is orthogonal. Okay, I think maybe you realize that, remember that formula said that if x is a vector x and qx have the same length, so that's what's going on here. So in that case, we go back up here. We can see that if this square and this square add to 1, and the lambda 1 is bounded above by lambda 2, so the biggest this can be is lambda 2 times 1, and the smallest this can be is lambda 1 times 1, right? Because lambda 1 times 1 is going to be bounded by lambda 1, well, it's equal to x squared plus y squared, which is less than lambda 1 x squared plus lambda 2 y squared, which is bounded by lambda 2 x squared plus lambda 2 y squared, which is lambda 2 times 1. Let me factor stuff out. And this is the same thing as, if this will be, these should all be primes, I guess. But then, and then this we know is equal to ax squared plus bxy plus cy squared. Okay. So that, and now we can also see that we get equality when we can tell exactly what values give us these max and mins. If Q1, remember Q1 is Q1 and Q2 are the column vectors. For Q, this corresponds to, this is the eigenvector corresponding to lambda 1, this corresponds to the lambda 2, and so we have, we can see, we'll go back up here, that we will get, can get lambda 1 when x prime is 1 and y prime is 0. That will give us lambda 1. Well, when will that happen? That x prime, y prime equals 1, 0 if and only if q transpose xy equals 1, 0. That's how we defined x prime, y prime. And then we can multiply by the inverse of q transpose, which is just q, and so we get xy equals q times 1, 0. And this is just, when you have a 1, 0 here, that plays the role of E1, the standard basis vector, and that's the first column of Q, which is Q1. And then similarly, we'll get a maximum when x prime is 0 and y prime is 1, right? So that happens when x prime, y prime is equal to 0, 1, which means that xy is going to be q times 0, 1, which is q2. So that's why. So we can just take the coordinates of these normalized eigenvectors, and that tells us on the circle given by x squared plus y squared, that will tell us what values of xy will give us this minimum value and the maximum value. All right. So let's just do an example right here to put this into practice here. So if we look at here we have an example. We have x squared plus 4xy plus y squared. Okay, it's binary quadratic form. The matrix corresponding to this is 1, 2, 2, 1. And the 2 comes from, that's 4 divided by 2. Okay, so that's our MF. And we want to find the characteristic polynomial. So that's 1 minus lambda, 2, 2, 1 minus lambda. This is going to be 1 minus lambda squared minus 4, which is lambda squared minus 2 lambda plus 1 minus 4, or lambda squared minus 2 lambda minus 3. And this luckily factors very nicely as lambda minus 3 and lambda plus 1. So this means that our eigenvalues are going to be 3 and negative 1, and we'll take lambda 1 to be the smaller one. This is negative 1, and lambda 2 is equal to 3. Okay. When we'll do lambda 2 equals 3 first, we plug in the 3 here, we get negative 2, 2, 2, negative 2. And it's pretty easy to see that 1, 1 is going to be the eigenvector, right? So we can normalize this, and we get Q1 will be 1 over square root 2, 1 over square root 2. And then when lambda 1 equals negative 1, we plug that up here. 1 minus negative 1 is 2, so we get 2, 2, 2, 2. And again, it's easy to see that negative 1 will be the eigenvector. So we can normalize that. We get Q2 is this, 1 over square root 2, negative 1 over square root 2. And in this case, so Q is going to be 1 over square root 2, 1 over square root 2, 1 over square root 2, negative 1 over square root 2. Okay, in this case, it is not only is Q orthogonal, but it's also equal, it's also symmetric, it's equal to its transpose. So we can just let x prime then become 1 over square root 2 x plus 1 over square root 2 y, and y prime will be 1 over square root 2 x minus 1 over square root 2 y. All right, so, but the thing here is our eigenvalues are, we have one negative eigenvalue, one positive eigenvalue, so this means that we have an indefinite quadratic form. And we can see that when x squared plus y squared equals 1, we can see this quadratic form is bounded by these eigenvalues 3 and -1. And in particular, we can see that this will be equal to -1 when x equals, well, -1 corresponds to this eigenvector. So this is x equals 1 over square root 2, y equals -1 over square root 2. And this is equal to 3 when x equals 1 over square root 2, y equals 1 over square root 2. You can also see, you can check this for yourself. When you plug in, like if you plug in these values, you'll get 1/2 plus 2 plus 1/2, and so that's 3. When you plug in these two values, you get 1/2 minus 2 plus 1/2. That'll be -1. Okay, so that's how that works. So that's basically what you will be doing. So just going to take a break for a minute, and then we'll finish up these notes.